Hey everyone, and welcome back to The Explainer. I am absolutely thrilled you're joining me today because we're going to unpack what is, in my opinion, one of the most fascinating topics in all of computer vision. We are looking at the incredible evolution of face detection algorithms. We'll be tracing this whole journey, right from the classical breakthroughs that made the tech even possible in the first place, all the way up to the massive deep learning showdowns that are dominating the field today. It's really this amazing story of human ingenuity, massive amounts of data, and our constant push to get machines to see the world exactly the way we do.
Okay, so let's dive right in by asking a pretty foundational question. How does a machine actually know what a human face looks like instantly? Have you ever stopped to just consider the absolute magic behind your smartphone camera? You point it and boom, it draws a perfect yellow box around your friend's face before you even snap the photo. Or how a security system can instantly spot a specific person in a completely chaotic, crowded train station. For a computer, isolating this distinct, constantly moving pattern of a human face amidst all that background noise and weird lighting, well, it was once considered an almost impossible computational problem. So, to understand how we actually solved it, here is our agenda for today. First, we'll look at the Viola-Jones breakthrough. Second, the deep learning era. Third, we'll do a speed versus accuracy showdown. And finally, we'll talk about choosing your ideal algorithm. Let's get into it.
Starting off with Chapter 1, the Viola-Jones breakthrough. This was truly a classical revolution.
So we have to rewind the clock back to 2001. And honestly, we have to treat the work of Paul Viola and Michael Jones with immense respect here, because before them, real-time face detection, it was largely just impractical. I mean, look at this number, 15 frames per second. Their algorithm was hitting 15 frames per second on 384 by 288 pixel images, and get this, they were doing it using a standard 700 megahertz Intel Pentium 3 processor. On early 2000s hardware, hitting that processing speed was practically a miracle. It essentially proved for the first time that machines could track faces in real time without needing an absolute supercomputer to do it.
So how on earth did they pull that off? Well, before AI could just learn features all on its own, human engineers actually had to handcraft them. Viola and Jones used these things called Haar-like features. Essentially, these are specific black and white rectangular templates. The algorithm simply calculates the difference between the sum of the pixels under the black rectangle and the sum under the white rectangle. And since human faces are generally regular, like, the eye region is typically darker than the upper cheeks, these templates could actually characterize facial patterns. Now, to make this lightning fast, they invented this brilliant trick called the integral image to compute these features at a massively reduced computational cost. Then, they used a committee learning algorithm called AdaBoost to sift through hundreds of thousands of possibilities and select only the absolute best features.
And if we look at the training process, it's pretty wild. On one side, we have the positive examples, these perfectly cropped 24 by 24 pixel grayscale images of human faces. And on the other side, the negative examples, just completely random non-face images. The Viola-Jones algorithm had to be painstakingly trained on thousands of these images just to minimize false negatives and false positives. But here's the catch. This classical approach definitely had its limits. It was strictly designed for full view, frontal, upright, and, perfectly lit faces. Which brings us to Section 2, the Deep Learning Era. Enter CNNs and beyond.
Because frankly, handcrafting those Haar-like features just couldn't keep up with messy real-world variables. We're talking weird camera angles, awful lighting, partial occlusions, you name it. We needed a total paradigm shift. And that shift was convolutional neural networks, or CNNs. Instead of engineers basically guessing what makes a face, these deep learning algorithms just figure it out themselves by churning through millions of images. And here are the modern heavy hitters we're looking at today. We've got YOLO, which is famous for framing object detection as just a single regression problem. RetinaFace, which manages to do localization and alignment in a single pass. MTCNN, which uses this really cool cascaded structure to detect faces and align facial landmarks at the same time. SSD, which perfectly balances speed and accuracy by skipping complex region proposals. And lastly, the tiny face detector, which is, specifically built for exactly what it says on the tin.
All right, Section 3, speed versus accuracy. Time for the showdown.
So, to find out who actually wins this heavyweight fight, researchers tested these models using the wider face benchmark dataset. Now, this is the absolute gold standard for testing varied poses and really severe occlusions. If we look at inference speed, we're measuring frames per second, or FPS. And what jumps out immediately here?
YOLO's absolute undeniable dominance. I mean, it is processing an astonishing 80 frames per second on a GPU and 25 on a CPU. It's literally leaving the others in the dust. And that's because YOLO processes the entire image in one single pass, rather than a clunky two-stage approach, so it is breathtakingly fast. If you were building, say, a live security feed or an automated surveillance system where you literally cannot afford lag, YOLO is, hands down, your top choice.
But hey, speed isn't everything, right? If we pivot over to detection accuracy, which is measured in average precision, the story completely changes. YOLO drops down to 0.88, while Retina Face comes in and takes the crown, with a massive 0.93 average precision score. Retina Face does this because it utilizes dense regression and incredibly robust feature extraction. It actually understands the context of the face within the image, which allows it to perform exceptionally well even under highly challenging circumstances like extreme shadows or when half the face is covered up.
And you know, this right here really highlights the ultimate trade-off in all of computer vision. You very rarely get everything for free. You almost always have to trade computational power for either speed or accuracy. YOLO gives you that maximum speed through its single-pass regression, making it absolutely perfect for real-time video. But Retina Face, that gives you maximum accuracy through dense regression and context sensitivity. That makes it ideal for high-stakes tasks. Think biometric authentication, or just unlocking your phone, right? Situations where a false positive is a massive security failure.
Which leads us perfectly into Section 4, choosing your ideal algorithm and matching your specific need to the right model.
Because out in the real world, best is an entirely subjective word. You really have to match your model's architecture to the physical constraints of your hardware and the specific environmental challenges of what you're trying to build. So let's synthesize this into a quick decision matrix. If your primary requirement is maximum speed, your ideal model is YOLO, perfect for something like real-time surveillance. Now, if you absolutely need the highest accuracy, you're going to deploy Retina Face, which is non-negotiable for things like biometric face unlock. But what if you're trying to analyze a massive, crowded sports stadium? You need to find small or distant faces. Well, the data shows the tiny face detector is optimized perfectly for crowd analysis. And finally, if you know you're dealing with partially hidden faces, say people wearing heavy scarves, medical masks, or big sunglasses, MTCNN really shines in occlusion handling. That's all thanks to its cascaded structure that refines its detection in stages.
So, looking back, we've come incredibly far from the 15 frames per second on a Pentium 3 that Viola and Jones pulled off. But this evolution, it is far from over. As AI pushes relentlessly onto edge devices, I'm talking smart glasses, autonomous drones, ultra-lightweight mobile phones, we are entering this new era where we have severe constraints on power, but practically limitless demands on performance. So I want to leave you with this thought to chew on. What is the next breakthrough hybrid model going to look like? What happens when our everyday, tiny devices demand maximum Retina Face level accuracy at YOLO level 0 latency, all while running on a battery the size of a coin? The next revolution in computer vision is literally just around the corner, and I cannot wait to see it. Thank you so much for joining me on this explainer.